about confidence intervals, and there's actually three different sections in chapter 7. Um, and the first one is over confidence intervals for population proportions. 7.2 is for population means, confidence intervals for population means, and then the third section is confidence intervals for standard deviations or variances. But we're just going to look at 7.1 today. So the idea of chapter 7 again is finding this thing called a confidence interval. And in 7.1, we're going to find a confidence interval for a population proportion. And so I have an example here. I want to go over and show you how this works. Okay, so this one says, my drug is used to prevent blood clots in certain patients, and in clinical trials, they tested 4,844 patients were given the drug, and 113 of them developed adverse reactions to it and had nausea. And we're supposed to construct a 95% confidence interval for the proportion of adverse reactions. So what's going on here is we're trying to estimate the actual proportion of people that would develop nausea as a side effect to being treated with this drug. And to do that, we can't look at everyone in the population, so we're looking at a sample of people, right? And so our sample consists of the 4,844 people, and it just so happens 113 of them develop nausea. So you've got, so let me put this on the notepad. Okay, so the population would be anyone that's given the drug. There's a certain percentage that would develop nausea, which we're going to call P, and that's called the population proportion. And because the population is so big, this is the parameter that we don't know. We're trying to estimate. And we're estimating it by looking at the sample. And of course, here we're sampling, I think it was 4,844 people. Let me double check that. Yep. And 113 of them developed nausea. So, of course, we use N for the sample size. So that's the size of the sample. And then we're going to use X for the number of people that develop nausea in this case. So 113. Okay. So the first thing we're going to do is actually find what's called the sample proportion. And the symbol we use for that is P with a little hat on top of it. So sometimes it's called P caret or P hat. That's a little caret symbol. If you don't have the hat on it or the caret symbol, then it's the actual population proportion. If it's P with a little caret on it, then it means the sample proportion. And of course, the sample proportion is just X divided by N. So 113 divided by the 4,844. And this is going to be our best, what's called our best point estimate for the real P. So if you want to estimate what this number is right here, as a single number, then you're going to look at the sample proportion. Okay, so P hat is the best point estimate, is what we call it. We call it a point estimate, but it's just, we're trying to estimate this as a single number. If we want to do that, then the best number to use would be P hat. Okay. And so we can put that in the calculator and see what that is, just to give it a number. So 113 divided by 4,844 happens to be about 0.02. 33 if you round it off. So It's about 2%, a little more than 2%. Okay. So what that's telling us is about, if you look at the 4,844 people that we sampled, that is the percentage that developed nausea in our sample. Now, that doesn't mean it's the same percentage that would be in the population. That's going to be what we're going to use to estimate it, right? The actual population proportion would only be known is if you sampled, everyone in the population, right? You gave them this drug and you determined what percentage developed nausea. That would be the actual population proportion. But since we don't know that, we'll probably never know that. That's the population's too large. This would be our best estimate for what that number might be. Okay. And that's called a point estimate. Now, of course, when we go into later sections, we'll be estimating population means, and we'll use the sample mean to do that. And then when we get to standard deviation, when we try to estimate a population standard deviation, we'll look at the sample standard deviation. Okay, we'll get to those. Those are the other two sections. Okay, but honestly, statisticians don't like using point estimates to estimate these sort of things. They prefer to estimate these parameters, like this population proportion, using what's called a confidence interval. So in this problem, I guess part A is find the point estimate, but then in part B, they're going to want us to find, so let me put this in. Oops. Rounded to 3 decimals, sorry. So the part B, they want us to construct, well, they want us to find the margin of error, but they want us to construct a 95% confidence interval instead of just the point estimate. So, like I said, statisticians don't really like estimating these numbers with a single number. What they prefer to do is estimate it with a confidence interval. It's a better way of estimating this population proportion. Okay, and so when we do this, we need to find, every time you find a confidence interval, there's an associated margin of error. So we're going to find the margin of error first, which we're going to use a capital E for. And there's a formula for the margin of error depending on what situation you're in. So for the population proportion, the margin of error formula looks like this. It's Z sub alpha over 2, and I'll explain what this is, but this is a Z-score, and then this is a subscript, which I'll talk about in a second. But it's a Z-score, okay? And then you multiply that by the square root of P hat times Q hat over the sample size, N. And of course, we know what P hat is, right? This is P hat. Q hat is simply 1 minus P hat. In other words, the percentage of people that develop nausea as an adverse reaction in the sample. Okay. And then N, of course, is the sample size. The hardest part of this is finding this is a little Z-score. Okay. And so let me show you how to find that. First of all, the alpha is the total area in the tails. And then this is actually alpha divided by 2. So we're going to find whatever the total area in the tails are, we're going to divide it by 2 first. And that's going to be subscript for this Z-score. And this is the area to the right of the Z-score. So that's what the subscript stands for. It's like area to the right. Okay. I'm going to draw a picture and kind of show you how this works. So ultimately, we end up with, have to have these p hat values that end up having to be pill-shaped for this to work. I'm not going to go into that detail, but you have to know that they're bell-shaped. And then when you convert them over to z-scores, and you end up getting standard normal bell when you do this. And if you remember, standard normal bell, of course, is bell-shaped, and the center is at 0, and then the standard deviation is 1. But then ultimately, these are z-scores down here. And if you remember, this side you have positive z-scores, and on this side you have negative z-scores. Of course, 0's in the middle where the peak of the bell is. And so what this refers to is every time you do a confidence interval, you have to determine what level of confidence you're going to use. So they said to use a 95% confidence interval here. Now I'll just tell you some of the more common ones are 99%, 95%, and maybe 90%. Those are pretty common. But you have to know up front what level of confidence you're going to use for your confidence interval. Okay. So in this case, they say 95%, which you want to turn that into a decimal. So 95% is the same as 0.95. Then alpha is 1 minus the 0.95. So it's 0.05 in this case. So what's going on here is we want to isolate the middle 95% of this bell. The middle 95%. So I'm going to shade that in here. The total area in this is 1, if you remember, right? The total area underneath this standard normal bell is equal to 1. And we're just going to look at the middle, 95% of that bell. So the middle 0.95 of it. And I want it to be in the middle. And so alpha is what's left over. This is the middle 95% of the data. And that means there's, 5% left over for what we call the tails. So you have a right tail over here and a left tail over here. The area in these two tails together adds up to 0.05. What's left over, right? Because the whole thing is equal to 1. And so alpha is always that area that's left over for the tails, right? It's the total area in the two tails. Then we want this to be the middle 95%. So we want the same amount of area in the right tail as in the left tail, and that's why we have to divide this by 2. Okay, and when you divide that by 2, you get 0.025. So essentially, that's how much area you have in each of these two tails. And that's why this is alpha divided by 2, right? It's not z sub alpha, it's z sub alpha divided by 2. So the way you do this is whatever the level of confidence is, like in this case 95%, you say 1 minus that level of confidence written as a decimal, and that gives you the area in the tails. And you have to divide that by 2 because you want each tail to have the same amount of area. And it's always a good idea to draw the picture of this so you can sort of visualize what's going on. And then this z sub alpha over 2 is actually the z-score. These are z-scores here, right? It's the z-score whose area to the right of it is that subscript. So we're looking for z sub 0.025. That's the subscript. And again, this subscript is how much area is to the right of the z-score. So if you look at this spot right here, the area to the right of that is 0.025. We want to know what that z-score is. That's what the symbol stands for. It's the z-score that has this much area to the right of it. Okay. And I'll show you how to figure that out. Of course, it's a positive number, right? Because it's above 0. The one over here is a negative number. It's below 0. That's not the one we want. This one has an area of 0.975 to the right of it. It's 0.95 plus 0.025. So that's not the one we're looking for. But I went ahead and drew it just so you could see the picture of what's going on. We want the one on the positive side, not the negative side, at least in this formula. Okay. So the easiest way to find this z-score is on the calculator. You may remember doing this from chapter 6. But if you go to the distribution button, so that's the button above the vars button, and you scroll down to inverse norm. So the first three here are all referring to normal distributions or bell-shaped distributions. You got normal PDF, normal CDF, and then inverse norm. Normal CDF allows you to find the area between two z-scores. Inverse norm is given an area, you want to find the associated z-score. And that's the situation we're in. That's why you're inverting it. You're going kind of backwards. So we're given the area and we want to find the corresponding z-score. That's when we use inverse norm. So just go to that. And then the calculator wants the area to the left of the z-score, which is kind of opposite of what we've got here in the picture. So you need the area to the left of this. Well, the area to the left of it, the area to the right of it is 0.025. And the calculator doesn't want the area to the right. Unfortunately, they program the calculator so that they always want the area to the left of it. So the area to the left of it, though, would just be 1 minus it. So you just have to say 1 minus 0.025. And so the area to the left of it would be 0.975. And that's what you want to put in for your inverse norm. Area to the left of the z-score, not to the right. And so if you do that, it'll give you the z-score. It's 1.96. Okay, so that's this z-score right here. Let me erase some of this. So that's what the z-score is equal to. Zero's in the middle, and there's a 1 here, and eventually you get to 1.96. Once you get to 1.96 at a particular z-score, that's when the area to the right of it is 0.025. Okay, and we just found that. That's the z-score that we need in this little formula. So I'm going to write that down. That goes right there. By the way, on the calculator, if you happen to mistakenly put in, let's say you did inverse norm of 0.025 by accident, you put in the area to the right when the calculator really wants the area to the left. Then you would get a negative 1.96, and you're actually getting this z-score on this side. So there's a symmetry to this. If this is positive 1.96, then this side would be negative 1.96, as long as the area in the tail over here is the same as the area in the tail over here, which it is, right? So if you happen to do that, just know that you've accidentally put in the area to the right instead, or sorry, the area to the left is 0.025, right? The area to the left is 0.025 would be like right there, and you're actually getting the z-score over on this side, which is a negative 1, and you really want the one on this side. So you should have put in 1 minus it. In fact, you could have just done that like this. You could just type in 1 minus 0.025 directly into the calculator like this. And so that's the same as 0.975, right? If you had just typed in 0.975, that's really the number you should have put in. You should have gotten positive 1.96. But if you mistakenly put in the area on the as 0.025, then you would get the negative of that. So just be careful. This number is never negative here in this little formula right here. It's always positive. Okay. All right, and then we're going to multiply that by p hat, which we've already found. And then times q hat, which, like I said, is 1 minus p hat. all divided by, and I'll calculate that in a second on the calculator, divided by the square root of divided by the sample size. Okay, and then I just got to put in this number here. Let me just see what that is. So 1 minus p hat gives you q hat. So q hat is, 0.9767. So about 2.3% developed nausea in the sample. About 97.7% did not develop nausea. That's what q hat is. Okay, and then you just basically have to calculate what this number is, and that gives you what we call the margin of error. So I'm going to go ahead and do that on the calculator and just see what we get. Okay, so 1.96. Actually, the easiest way to do this is to find the square root first, or actually find the number inside the square root first. I'm going to do it that way. That way I don't have to use all these parentheses. So p hat times the q hat, 0.967, or 0.9767, sorry. Multiply those together, and then divide by the sample size, 4,844. And then you get this number, and notice it's got this e to the -6. That's scientific notation. Tells you how many places to move the decimal. So, and if it's negative, you move it to the left, and if it's positive, you move it to the right. So this means you need to move the decimal 6 places to the left. So it's actually like 0.0000467. If you were to write it out, we don't need to write it out. But just as an FYI, this is scientific notation. So it's a really small number, right? You have to actually shift this 6 places to the left. Now, if it was positive, you would shift it, like if it was a positive 6, you would shift it 6 places to the right, and it would be a really large number. I'm not going to write it down. We're going to take the square root of that number, and then the square root is a little blue square root right there, right? It's above x squared, but make sure you don't want to square it. You want to take the square root of it. So the number above it, or the thing above it. So the square root looks like that. And then you don't have to type this in. You could use your little answer button down here, and it takes the previous answer, and it's going to take the square root of that previous answer. So you don't have to type this previous answer in. It's just taking it automatically in the calculator. And so if you take the square root of that number, you get 0.02167, right? And then we've got to multiply that by the 1.96. Okay, and so the margin of error is 0.004. Okay, let me go ahead and put that in to make sure we've got it correct. I did round off a bit, so maybe there's a rounding problem. Okay, so that's the margin of error. It's a very small number. Then the final thing is to actually find what we call the confidence interval. And essentially what you do now is this is your point estimate, right? So the part A was like find the best number, right? If you had to sort of give me a number that you think this is, what's your best estimate for what this number is, you would say 0.0233, right? About 2.3% of the population as an estimate would develop nausea based upon my sample proportion. But now if you want a confidence interval, and we're doing a 95% confidence interval, then what you do is you take this point estimate at and we're going to subtract the margin of error, and we're going to also take the p hat and add the margin of error. And this is going to be like a low number in our interval, and this will be the high number in our interval. And that's going to be our confidence interval for the real p. So it's our estimate for p as an interval. So p's in the middle. So it's going to be, p hat is this number here minus the margin of error. And then on the other side, we take p hat and we add the margin of error. And that'll be your high number in the interval. This will be your low number. So let me just see what that is real quick. So 0.0233 minus the margin of error, 0.004. On the low end, it's 0.0193. And on the high end, if you add those, it's going to be 0.0237. Wait, yes, but I'll double check that just to be sure. 0.02737. Okay. Or 0.0223 plus 0.004. So you get 0.0273. Sorry, I have that backwards, 73. Okay, so again, once you find the margin of error using this little formula, you take your point estimate and you say you add the margin of error to that. So here's my point estimate, and I added the margin of error. That gives me this high number. And then you take the margin of error and you take the point estimate and you subtract the margin of error, and that gives you the low number. And then this is your confidence interval. And so the way we interpret this is we're 95% confident that the p that we're trying to estimate is somewhere between those two numbers. So between these two numbers. And so that's how you find a confidence interval. But the reason that the confidence interval is better than the point estimate is because if someone comes to you and says, what do you think this number is up here? Your point estimate, you would say, I think it's somewhere close to 0.02333, right? This number here, about 2.3%. But if someone comes back to you and says, well, close to 2.3%, what do you mean by close? That's a very vague term. If you want to be more precise about what you mean by close, you would have to come up with a confidence interval. So my response to them would be, how close? Well, okay, I can now say that I'm 95% confident that this p that we're trying to estimate is between these two numbers. And that's how close I think it is to 0.0233. So it's a better way of estimating, actually. Rather than estimating it as a single number, it's better to estimate it with a confidence interval. Because again, it gets to this idea of like, if someone says, what do you think this number is? Here, we would say, I think it's somewhere close to 0.0233, but what do you mean by close? That's a vague term. Close, what do you mean? This is more precise. This says that I'm 95% confident that it's between these two numbers. Okay. Now, the level of confidence is arbitrary. You could have done, like I said, a 99% or 90% confidence interval. And then this margin of error would change a little bit because the z-score would change. But then, whatever level of confidence you're using, ultimately, once you get your confidence interval, that's the level of confidence you have in your estimation here for p. So In this case, we're 95% confident that P is in this range, okay? Okay, so let me just plug this in and make sure we got it correct. So the low number was 0.0193. And the high number was 0.0273. Double check it. Yep. Okay, so there might be a rounding problem. Or I'm supposed to round to 3 decimals, right? So it should be, if you round to 3 decimals, it would be that, and 3 decimals would be that. So let's see. There you go. Okay, so that's kind of how you work these out. And then the final thing here, part D, is interpreting it correctly. So you would say, which one is it? So one has 95% confidence that the interval from the lower bound to the upper bound actually does contain the true value of the population proportion. So it's B, right? Okay. All right. So that's how you do that kind of problem. Now, there's one other type of problem here that we need to talk about. And it has to do with what's called sample size determination. This is probably the third one to do. Let me see. Yeah. All right, so this is related to confidence intervals. It's called a sample size determination problem. And so the idea here is we're trying to determine what's how large of a sample do I need to take in order to get a certain margin of error or less, like within a certain margin of error. So if you think about it in the real world, you need to know how big your sample is first, right? You have to decide how big of a sample to take. That's one, because here's a large population. I'm trying to estimate like the population proportion. I first have to decide how many people I'm going to sample from the population. So how do you determine that? Well, you decide what level of margin of error you want, or how, what's the margin of error you want to be within. And then once you know that, and also what level of confidence interval you're going to end up with, you want to use. Once you know both of those things, then that will determine how big the sample has to be in order to get that margin of error to be within whatever amount you want at that level of confidence. So in this particular problem, if you read through it, they're basically saying how many passengers, air passengers, must you survey if you want a 95% confidence interval ultimately, where the margin of error is within 4.5% of the true population percentage. So this is, you want your margin of error to be within 4.5% and ultimately end up with a 95% confidence interval. And the question is, how big of a sample do you need to take in order for that margin of error to be within 4.5% of the true population proportion? Okay, so how do we do this? So essentially, this is what's going on. Here's your margin of error formula. What I'm going to do here is I'm going to actually solve for n because that's what we want to know algebraically. And so to solve for n, remember when you do something like this, whatever you do to one side of the equation, you can do to the other. it'll still be equal. So the first thing I'm going to do here to get in by itself is just divide both sides by this z-score. Now remember, whatever I do to one side, I can do to the other, right? So I'm dividing both of them by z. That cancels this out. Whatever this number is, it's canceling out with this number. And you're left with e over z is equal to the square root. And then I'm going to get rid of the square root by squaring both sides. So I'm going to square this side. I'm going to square this side. And if you may remember this, if you square a square root, let's say you take, let's say you have the square root of 9, which happens to be 3. If you were to square this, then the square root of 9 is 3, but then 3 squared is 9. So when you square a square root, they essentially cancel out, right? And you're left with the number here. So the reason I'm doing this is I want this square root to cancel out, so I'm squaring it. And when I do that, you're just left with what's in here, right? P hat, Q hat over N. Okay, and then I want to get this in by itself. The fact that N is in the denominator is kind of a problem. I don't want it in the denominator, I want it in the numerator, but that's easy to fix. I could just multiply both sides by N, and these will cancel out. And now I'm left with N times this E over Z squared is equal to P hat Q hat. And then the last thing I'm going to do is multiply by, well, you can actually think of this. Let's just do this. This, when you square this, you can square the top and then the bottom. So it's the same as E squared over Z squared. Right? If I have like 3/4 squared, that's the same as 3 squared over 4 squared. So think of it that way. Instead of E over Z squared, you can think of it as E squared over Z squared. And the reason I want to do that is because I want this n by itself. And so I'm going to multiply by the reciprocal of this on both sides. So the reciprocal would be Z squared over E squared. And what that'll do is the Z squares will cancel. You got one on top and one on bottom, and then the E squares will cancel, right? Because you got one on top and one on bottom, and that'll leave you with N. And so N is ultimately of course, that's a subscript, alpha over 2. It's Z over E squared times P hat times Q hat. Okay, and that is a formula for determining the sample size. Okay, now I've derived this formula for you algebraically, so you can just use this formula in the future, right? You don't have to derive it. I just wanted to show you, but it does come from, right? I mean, where did this come from? It came from this margin of error formula that we had here, right? Okay, so this margin of error formula, that's how we determine margin of error. It's a relationship actually between the size of the sample size and the margin of error, right? The larger the sample size is, since you're dividing by n, the larger this number is, the smaller the margin of error is. Okay. But if you just want to figure out what the sample size is and you're given the margin of error that you want, you can determine how big of a sample you need for that margin of error. That's what this formula is kind of telling us. So I'm going to go through and work out the problem now using that formula. Okay, so let's go back to the problem. So this one says we want the margin of error to be within 4.5%, and we want ultimately we want a 95% confidence interval with that margin of error, or within that margin of error. So we want the margin of error to be less than 4.5%. Okay, which you want to write as a decimal. So 0.045. Just move the decimal 2 places to the left. And so in the formula, it's going to be this number. Z-score is associated with the level of confidence. So remember, ultimately they want a 95% confidence level. And if you go and do everything we did before, same sort of stuff, you isolate the middle 95%, and then you find alpha. And that's the total area left over in this tail and this tail combined. It's 0.05. And of course, you want the amount to be the same in each tail, so you have to divide by 2. So same thing we did before. And you end up with the same number. You go and do inverse norm of the area to the left, and you end up with 1.96. Same thing we had before. This one's negative 1.96, but we want the positive one. Okay, so this number here is always associated with the confidence level. In fact, if it's a 95% confidence level, you'll always get 1.96 for this number. If you change it to 99%, then you're going to get a different number. You'll have to figure out what that is. If you do a 90%, you'll get a different number. You have to figure out what that is. But for 95%, it's always 1.96. Okay. And now we need to plug in p hat and q hat. And this is a bit of a problem because the only way you'll know what p hat and q hat is if you actually had a sample, because these are the sample proportions, right? This is the proportion that would develop nausea. This is the proportion that would not develop nausea. The only way you would know that is if you actually took a sample. So maybe you haven't taken a sample yet. Maybe this is the first time you're sampling something. If that's the case, these numbers always add up to 1. If you think about it, if 60% develop nausea, then 40% don't develop nausea. You have to account for everything, right? So if this is 60%, then this has to be 40%, right? So it always adds up to 1. So the best thing to do here is, if you don't know what these numbers are because you haven't taken a sample yet, is to split it down the middle. We're going to assume that they're both 0.5 if we don't know what they are. That's the best thing to do in this situation, which adds up to 1, right? So 50% here and 50% here. If you don't know what the numbers are. Now, if you know what p hat and q hat are from a previous study that you've done, then maybe you want to use those numbers. But if you've never done a study before and you don't know what these numbers are, then we just say half here, half here. Okay. And this will give you, let's see, it's in the calculator. So 1.96 divided by the margin of error. Gives you this number, but then you have to square it. And then the square is right there. So the answer squared would be that number times p hat 0.5 times q hat, which is 0.5. And so we end up with 474.27. Now, the thing about this number is it represents people. And so it's either 474 people or 475 people. You can't survey 0.27 of a person. So the question is, which one should we go with? You can't go in between these two numbers, right? You can survey 474 people, or you can survey 475 people, but you can't survey 474.27 people, right? This is a discrete number because it represents people. So the question is, which one do we go with? Well, remember, the problem says you want to be within this margin of error. You don't want to be above it. You want to be within it. So within means less than this number, right? So this is this. If n is equal to this, that is when e is exactly 0.045. In fact, if you want to go back to the original formula, margin of error, which was this. Okay, if you plug 1.96 in for z, and then 0.5 in here for p hat, and 0.5 in for q hat, and then plug in 474.27 for n right here, and that's when you get e to be exactly 0.045. I want it to be within 0.045. So which of these two numbers is going to cause it to go within 0.045? And the answer is the larger one. This is going to be, this will give me a margin of error of a little bit less than 0.045. And this one will give me a margin of error a little bit more than 0.045. And you can test this on your own if you want. The idea is that if n is a little bit bigger, right here, right? Remember, this is when e is 0.045, that's when n is this number. If I go a little bit bigger, well, that means I'm dividing by a little bit bigger number, right? N is on the bottom. So if I'm going to divide by a little bit bigger number, that's going to force the error to go down a little. So it's going to be a little bit less than this if I go up the n. And if I go down with n, right, if I let n be a little bit smaller than this number, then I'm dividing by a smaller number, and the error is going to go a little bit up. So that's why it's going to be a little bit bigger than 0.045. So the answer is I need the bigger one. I need n to be a little bit bigger because that forces the margin of error to go a little bit down because I want it to be within 0.045, right? So rule of thumb here is always round this number up. Always round up to the next integer, okay? So, if this was 474.01, we'd still round up to the next highest integer, 475. Even though 474 is closer, technically, you want the margin of error to go down, so you would have to go up to 475. You would not want to go to 474 because then that would force the margin of error to go above what you wanted. So it's always a good rule of thumb is to round up, even if it's this close, right? I mean, this looks like you should say 474 because it's so close to it. But in this situation, it's better to round up to 475 to force the margin of error to go below this amount. Okay, so let's go to the problem. What did we decide it was? 475. So notice in part A, it says, assume that nothing is known about the percentage of passengers who prefer aisle seats. So we don't know what, in other words, we don't know P hat or Q hat because there's no previous study. Okay. Now, part B says, assume that 32% prefer the aisle seat, which is what this problem is trying to estimate. Is like what percentage of people prefer the aisle seat on a passenger plane. So I guess what they're saying here is we have a previous study where we happen to know that based upon this previous study that we think about 32% of passengers prefer the aisle seat. So we have an estimate for what P hat might be. So the only difference now is when you do this problem in part B is we can now, instead of like, since, before we didn't know what these numbers were, we said it was 0.5 and 0.5. We can now say, well, we kind of think that this number is close to 0.32 because 32% favor the aisle seat. And we know what Q hat is because it's 1 minus P hat. In other words, I guess 68% do not prefer the aisle seat. So then you just plug those numbers in instead of 0.5 and 0.5. So going back to the formula, we still want a 95% confidence interval. So this z-score is still going to be 1.96. So that's not going to change. And we want the margin of error to be within 0.045. So that doesn't change. But we now have an idea of what these numbers are. So we're just going to use, 0.32 and 0.68 for those. Okay. It's only if you know what, if you happen to have an idea of what these numbers are from a previous study. If you don't, then like I said, you would just use 0.5, 0.5, split it down the middle. Okay. So let me just see what that is. Okay, so 1.96 divided by the margin of error. And then square that number. And now this time we multiply by 0.32 and then 0.68 instead of 0.5 and 0.5. And this time we get 412.8. And of course, like I said, we want to round this number up. So we're going to round it up to 413. And you can see that saves you a little bit of, the sample size is not quite as large. Like if you didn't know what these numbers were, you would have to sample 475 people. If you have an idea of what they are, then it drives this number down a little bit. In other words, this is the worst case scenario. That's why we used it. If we don't know what these numbers are here, then we're just going to use the worst case. The worst case would be that they're split down the middle, 0.5 and 0.5. That's because, let's say it was 0.4 and 0.6. When you multiply those two together, you get 0.24. When you multiply 0.5 and 0.5 together, you get 0.25. So when you multiply these two numbers together, right, it's even smaller than 0.24. So this is largest this number will ever be right here is when they're both 0.5, right? You get 0.25. Anything less than that, like 0.4 and 0.6, would drive this number down, and that gives you a smaller sample size. Okay, so it saves you money, right? Because you don't have to sample as many people. So it's not a big amount. It's like 50 or 60 people, but nonetheless, it does save you a little bit. Okay, so let's just see if that's right. 413. Yep. Okay. Okay. So I don't know, Shamika, I kind of went over the two big problems here. Do you have any questions about any of those? We can go back. I still have the work if you want to talk about them.
No, I'll have to work them out tonight and then go from there.
Yeah. What you can do is I've recorded the video, so if you want to kind of go back and rewatch this to kind of get a digest it when you're working the homework, you could probably do that. And then you could also just email me, right, if you have questions about it.
Yes, sir.
Okay. One other thing I want to mention, and I'll let you go since we're almost out of time, is the initial problems here. This one, start off slow, and they just say find the z-score first, because that's kind of the first thing you do in the formula for all the different kind of levels of confidence, just to sort of get you, because that's the hardest part in the formula. So you're going to kind of practice doing that first, get used to finding this z-score, and once you kind of get comfortable with that, right, they give you a couple problems, then you can actually do another one I did where you actually find the margin of error and the actual confidence interval. But you should practice finding this first, because this is the hardest part of it, okay? And then you can go from there. But anyway, if you have problems with it, just let me know, email me, or we can talk about it tomorrow as well.
Okay. Sounds
Okay.
good.
Okay. All right. I'll talk to you tomorrow then.
All right. Thank you.
No problem.
Bye-bye.
Bye-bye.